This talk is about how to build a programming system for graph pattern mining that is efficient and scalable on GPUs. And this is a collaborating work with Arvind. So graph is a data structure widely used to model interactions between certain objects of interest. For example, in a social network, we have vertices as the people and edges as the relationship between the two people, such as the friendship. And other examples include the recommender systems, protein networks in the biomedicine applications, and financial transactions graphs. So graph exists in numerous real-world applications. And graph pattern mining is to extract higher order information out of the graph data, instead of just looking at the vertices or edges. For example, we might be interested in finding a group of people with similar interest in a social network, like Twitter's who follows whom graph. And we can do friend recommendation by searching for this small pattern here. User A follows user B and user C. User B and C both follow user D. Then we might think that A would also be interested in D and recommend D to A. Another example is in the financial transactions graph, where we can do anomaly detection by finding this circular pattern here. Custom A transfer money to B, B transfers to C, C transfers back to A. And this is suspicious because it could be money laundering activity. So there are many more interesting applications in chemical engineering, online shopping, drug discovery, and so on. Despite its wide adoption, graph pattern mining is extremely compute intensive, which usually runs for hours or even days on the high-end CPUs. And in this work, we built G2 miner system that leverage GPUs to speed up the graph pattern mining algorithms. So the key challenge here is that the GPU performance optimization for graph pattern mining is very sophisticated due to multiple reasons. For example, graphs are sparse, and the GPUs are not good at processing sparse data, which makes it very difficult to program and optimize on the GPUs. In addition, the graph pattern mining algorithm itself is can be very complicated, and it generates intermediate data that needs careful memory management, which imposes another level of complexity to the problem. So how do we address this issue? Instead of hand optimizing for each specific graph pattern mining problem, our approach is to systematically automate the optimizations. The key insight is that in order to enable all the possible optimizations, our system should fully leverage the pattern, the input graph, and the hardware architecture information. Our evaluation showed that with automated optimizations, G2 miner is 5 times faster than the state-of-the-art GPU-based graph pattern mining system. So before we dive into the details of G2 miner, let's see what is the graph pattern mining problem. So we are given this data graph and a set of patterns, and the goal is to find all the subgraphs in the data graph that match any of the given patterns. So here's one example. We have a data graph with 5 vertices, and the pattern is a triangle. Then we need to find all the triangles in the data graph which are listed here. So graph pattern mining is a search problem. So to solve this problem, the first step is to define the search space. And this is done by building the subgraph tree. Let me use a simple example here to show how to build this tree. So in the subgraph tree, each node is a subgraph of the data graph. The root is an empty subgraph. At level 1 of the tree, each subgraph has 1 vertex. At level 2, it has 2 vertices, and so on. From level 1 to level 2, we add 1 more vertex, which in the original data graph is in the neighborhood of the parent subgraph. For example, here the parent subgraph is vertex 1. It has neighbors of 2 and 3 in the data graph. So 1 can become 1, 2, or 1, 3. Adding a vertex is called a vertex extension step, and we can keep extending the subgraph until the size of the subgraph is the same as the pattern, and then we can compare it with the pattern to see whether it is a match or not. And if the data graph or the pattern graph is very large, then we can imagine that this subgraph tree is a massive search space because of combinatorial explosion. And also, to build this tree, we need to maintain lots of intermediate data, which is shown in this figure. In order to reduce the search space, people have proposed all kinds of pruning schemes by leveraging the pattern structure, which we call pattern-aware pruning. A widely used pruning scheme is called symmetry breaking. For the same example in the previous slide, there is only one triangle in this data graph. But during the subgraph tree search, this triangle will be found 6 times. This is because we can perform the search in different orders. And to avoid this redundant enumeration, we can enforce an ordering between the vertices. And for this triangle pattern, we can which is called the symmetry order. So for this triangle pattern, we can define the symmetry order in this way. V1's ID smaller than V2's ID, smaller than V3's ID. And using this ordering as a constraint, there's only one triangle can meet the requirement, and all the other subgraphs can be just pruned. And notice that this ordering is pattern specific, which means that for different patterns, these symmetry orders are different. Except for the symmetry breaking, there are many more other pattern-aware pruning schemes exist in the hand-optimized applications. Even though pattern-aware pruning can reduce the search space, it's still a massive search and very slow. Another way to make it faster is to parallelize it. One attractive solution is to use the GPUs. But we know that the graphs are sparse, and this will cause a lot of issues on the GPU, such as the load imbalance, thread divergence, and so on. And also, we need to maintain the intermediate data, and we know that GPU has very limited memory capacity compared to the CPUs. So that requires us to carefully manage the GPU memory usage. Overall, in order to achieve this high performance, we need to implement sophisticated optimizations, which is quite difficult for the domain users who are not necessarily GPU programming experts. Instead of hand optimizing for graph pattern mining problems, case by case, we build a system G2 miner to simplify programming by automating the optimizations. Our key observation from the investigating a large amount of hand-optimized graph pattern mining application is that there is a lot of information in the pattern input data graph as well as the hardware architecture that can be leveraged to apply optimizations. But prior systems do not fully leverage this useful information, and so many optimizations are missing in these systems. In contrast, G2 miner is aware of all 3 aspects of information, therefore is highly optimized. So let's see how this information is made available in G2 miner. So we have the user-defined pattern here, and we have an input data graph. We target the GPU. So first of all, we have a pattern analyzer, which takes in the pattern, does analysis on it, and extracts useful pattern information out of it. It then generates a search plan, which contains the pattern-specific pruning scheme, such as the symmetry order. And this plan is then fed into a code generator, which generates the pattern-specific CUDA code that can run on the GPU. At runtime, we have a graph loader, which loads in the input graph and does pre-processing on the graph to reduce computation. And the loader can also extract useful input information and feeds it into the runtime system. So the runtime can use the input information to make runtime decisions specific to the inputs. For example, the memory allocation for the intermediate data. Meanwhile, the pattern analyzer will provide the pattern information to the loader and the runtime system. So the loader can perform pattern-specific pre-processing, and the runtime can enable pattern-specific optimizations. In addition, the GPU architecture information is used by the code generator and the runtime. So we can generate the GPU-aware code, and the runtime can enable GPU-specific optimizations. And by using all these 3 aspects of information, we can enable a lot of optimizations in our system, which are listed here. So this table shows that these optimizations can have different effects on performance, such as mitigating the divergence, improving load balance, and algorithm pruning. Some of these optimizations can also reduce the GPU memory consumption to enable larger data sets. And this table here shows that which information is required to enable each of these optimizations. And most of these optimizations are automated by checking the applicable conditions using the corresponding pattern input and the architecture information. And the last 2 need some simple user guidance. And notice that among all these optimizations, there are some existing optimizations that have been used in both the prior systems and hand-optimized applications. There are also optimizations that have not been used by any of the prior systems, but they have appeared in some of these hand-optimized applications, such as triangle counting. In our system, we generalize these optimizations so that they can be extended to other cases that satisfy the application conditions. We have also proposed the new optimizations which have never been used in either prior systems or hand-optimized applications. To better understand the optimizations in our system, let me show you one example about how architecture awareness can help improve performance. We know that GPUs are vector machines that are good at regular algorithms like matrix multiply. But for irregular algorithms, there is a thread divergence problem. Suppose the program contains a branch, and some of the threads in the warp go to path A, other threads go to path B. Then in this case, the hardware utilization is only 50% and usually leads to poor performance on the GPU. And this is known as the branch divergence issue. And for the irregular memory accesses, there's also a memory divergence problem. And for the graph pattern mining algorithms in particular, when we use multiple threads to perform the search in parallel, these threads will diverge significantly during the tree traversal. This is because different subtrees will have different neighborhoods due to the sparsity of the data graph. In G2-Miner, we mitigate this problem based on the key observation in the graph pattern mining algorithms, which is the fact that the set operations take the most of the execution time. For example, to find triangles, we need to compute this set intersection operation, which intersects the neighbor sets of two vertices to form the triangle. We observe that this observation takes most of the execution time for the triangle counting, and this observation is also true for the other graph pattern mining applications. And we did a providing with various patterns and data graphs, and this figure here should just show that roughly 80% of the total execution time is spent on the set operations. So based on this observation, we'll propose a two-level parallelism strategy for the GPU. First, we use the interval parallelism for the subtree traversal, where each subtree is assigned to a warp instead of a single thread. In this way, all the threads in the warp will perform the same subtree traversal, which avoids the divergence issue. And then we use the intra-warp parallelism for the set operations. Suppose we have two neighbor sets here, and we want to compute the intersection of these two sets. Then what we do is we let each thread in the warp to take one element in the first set, and then perform a binary search in the second set to check if it exists in the second set. And you can see that since these binary searches are performed in parallel, so that we can make the set operations faster. You might also have noticed that there is some redundancy because all the threads in the warp perform the same subtree traversal. But overall, it's a much better trade-off of GPU, given the fact that the set operations take the most of the execution time. And that is just one example of architecture awareness. You can find more details in the paper about how pattern and input awareness can help improve performance. OK, now let's look at how G2-Miner performs. We compare with the state-of-the-art systems, Peregrine, PBE, and Pangolin. So Peregrine is a CPU-based system, and all the other systems are GPU-based. In this figure, x-axis shows the different graph pattern mining workloads. Y-axis shows the execution time in log scale. Lower is better. So we can see that G2-Miner on GPU is 1 to 3 orders of magnitude faster compared to Peregrine on the CPU, thanks to the high efficiency we achieve on the GPU using these optimizations. And compared to the other GPU-based systems, we also can achieve significant speed up. In particular, we observed that the Pangolin fails to run most of these workloads because it runs out of memory for these large graphs. And in comparison, our system is able to run all of these workloads thanks to the optimizations that reduces memory consumption on the GPU. On average, G2-Miner is 5, 7, and 48 times faster than Pangolin, PBE, and Peregrine. To conclude, we point out that high-performance graph pattern mining on GPUs requires sophisticated optimizations. G-square miners systematically automate these optimizations by leveraging the pattern input and architecture information. Unlike prior systems that sacrifice performance for programming productivity, this work shows that we can simplify programming and achieve high performance at the same time. And that's all. Thank you.